according to how to say in English.
But Pythagoras doesn't sound anything like Pythagoras in Chinese.
Pythagoras is the name of the person?
Yeah.
Oh.
Like, what's Pythagoras in Chinese? Yeah, what's his name?
I don't know.
No, it's not. It's totally different. Is it?
We call that 勾五定理.
Yeah, does that not mean Pythagoras? That means something else.
Yeah,
it's not a name of a person.
In our Asian China, people.
They had this rule.
Yeah, they had. We call it different name.
Ah, so different person.
For Costco and Costco.
Yeah.
Go for 古代的. Go for 古报.
What's that?
Go say 古报.
Yeah.
We have that.
Yeah.
We call that as 钱. Therefore, we call it 勾五定理. 定理是.
Oh, so it's like 3, 4, 5.
Yeah, just 3, 4, 5.
Ah, okay. Okay, this makes sense now, because I thought it was the Chinese name for Pythagoras. But it has nothing to do with the person Pythagoras. Yeah, okay, interesting. Right, Newton's 3 laws. So as I was saying, we all know Newton and his name. And maybe some of you already know his 3 laws. We'll have a look at them. We've already done the second law. Does anybody know his first law?
Yeah.
Go for it.
Inertia.
Yeah, but give me a sentence.
An object that actually
Remain its motion.
Not quite.
will remain uniform.
Oh, it started well and now it's falling apart. Nailed it. Okay, not quite that. Close. Newton's first law. If a body's at rest, it remains at rest, or if it's in motion, it moves with uniform velocity until acted on by a force. So in other words, if it's at rest, it will stay at rest. If it's in motion, a uniform motion, it will stay in this uniform motion, unless a force is applied. And yes, Newton's 3 laws will be common in the exam. Can you all see? Okay. Could I? I suppose I could. Okay. Jerry, where's Bruce today? Bruce didn't get up. Nice. That's the same thing you didn't.
How do you know?
He told me. I told him maybe I will be late.
And he said, that's okay, I'm not going.
No, he said I'm not getting up.
He's not getting up?
I don't have that 9 a.m.
He looked out the window, he saw the rain and said,
No.
physics, rain? Tough call. Okay. We got this? Can I continue? Jerry, do you have this or do you need a minute? Sure. Have you all seen this law before in high school?
Yeah.
Yeah? Okay. Got it, Jerry? Yep. Okay. So, here is an example, a simple example with a little picture here I found that I thought it explains Newton's first law quite well. So, here's the football. It's at rest, and it will stay at rest unless acted on by a force, in this case the foot. Then, here's the ball in a constant motion. it will continue in this motion unless acted on by a force, in this case the net. Now it's not a perfect example because here the motion isn't really constant because the ball is fallen, but just as a rough idea, it'll stay at rest until a force acts on it. It will continue in a constant motion unless acted on by a force then. So I like this little picture because it kind of explains it quite nicely, Newton's first law. Okay, Newton's second law. We know this one because we did it recently. What is it? F equals ma. Or simply, in words, force is mass multiply acceleration. So if you can take this down, Newton's second law. Got that? Yep. Okay. And it's the only picture I could find. So force is mass multiply acceleration, which is a change in velocity. Okay, Newton's third law. Does anyone know this one? Go for it. That's the one. For every action there's an equal and opposite reaction. Got that? Yep. So here's a relevant example. In this example here, air comes out of the back of the balloon, and the result is that balloon moves forward. So the air coming out the back is the action, and the balloon moving forward is the reaction. And we'll actually see more situations like this today. Particularly when it comes to pushing against the wall and stuff like that. This is just a basic idea. Here's what I mean by reaction as well. We know that gravity acts on this, so that will pull it down. But when it reaches the table, it doesn't continue to fall. But gravity is still acting on it. So the only way it cannot continue to fall if there's an exactly equal force balancing this force. That's the only way it can stop moving. So this weight has a reaction when it's on the table, and this is called the reaction force as well. So when we say the reaction force, we usually mean the force that comes by from the reacting object. So in this case here, the table is reacting with the weight, reacting to stop the weight from falling. That is, by providing a reaction force. So the reaction force is the force provided by the reacting object. In this case, it's the table. So can you note this, please, a reaction force? Yeah. Got that? Continue. Yeah. Okay. So here's a simple example. We'll do it together. 20 kg is on the table. What is the reaction force? Okay, so this one. Yeah, that's all it's going to be. So here's our table. Here's our 20 kg. It has a weight of 20 mg. So the reaction force must be 20 g as well. What's that? 19,986? 96? Are you sure? I don't think it's that much. $196.2. Okay. That's an easy one to get started. So let's have a look at another one. Okay, so I'll let you read it and you can draw or write, and then I'll do this one. Did you draw this, Jerry?
We're doing just something now.
But it would make me happy if you draw it. Thank you. You do want to make me happy, don't you? Thank you. You drew this, KJ? Can I see? Just make sure you have the idea. Yes, and is that the force pulling up? Yeah. Did you draw, Jerry?
No.
Show me your picture. Is there a force going up, or is that going at an angle? Is this force at an angle or going up?
Going up.
Straight up? Yeah, you see this word here, vertically, means the force is straight up. He's pulling it straight up. You understand?
I thought it's double. It's double.
Double?
It's double.
How? He's confused me. I'm confused. Oh yeah, okay. Okay, that's a good idea. Alright, let's do this one now. So, whoops. What did I say it was? 200 kg?
Yeah.
And so here this is 200 G, and we have a reaction force, and also the man is pulling up with 1,000 newtons, was it? So what's the reaction force here? Yeah, now explain that there, Monica. Why are we saying R plus 1,000 equals 200 G?
Because the blood seems to move, which means there's an equal.
Yeah, it's not moving, so there's an equal force up and down. But why did you add the R and the 1,000 together?
The total force.
Yeah, it's the total force. So the total upward force equals the total downward force. So in this case, the R is actually up. Do you know where you're going?
We're looking for Cap 9, this one?
No, this is Cap 9, but you must have your timetable wrong, because we're in here
Until 10.
until 11.
11.
Until 11. Yeah. Are you too early?
No, we have class at 9:30.
Okay.
Sorry about this.
No problem. You said class at 9:30
Yeah.
in Cap 9? Anyways. What was he saying? Oh yeah. So the previous one was okay. So this will be 962 newtons.
Yes.
The answer here is the reaction force. Cool? Yes?
No.
No? What's confusing you?
Why R plus 1000 equals to...
Because the total upward force must equal the total downward force.
Can it be like less than the downward force?
Then the block would be moving, yeah. So if this was less than this, then the block is rising.
Okay.
Yeah. Yeah? Okay. Right. Again, please draw, and we'll do this one. So it's a little bit different now. My grammar's a bit messed up. I should really say a man begins to drag the block. We got pictures?
Yeah.
Okay. Got a picture, KJ? Yeah? Everybody's got a picture? Okay, so it's kind of the same as the last question, except with one key difference. He pulls at an angle of 45 degrees, 1,000 newtons.
Isn't it 200?
Is it? Oh, I wrote 2,000. Thank you. Okay. This is 200G. Right, so what do we have to do now that's different? Any ideas?
You that force equal to sine 45.
Ah, yeah, what's the verb for this now? Give me the verb. You mean, right, to do this, yeah?
The isolate.
That's not a verb. What's the verb? Somebody give me the verb. Oh, come on, Monica. I expected better from you now. You're practically a native speaker. Come on, what's the verb?
Resolve.
Resolve. Thank you, KJ. Resolve. Yes, Jerry, resolve. Okay. And we also have a reaction force present still as well. So what can we say this time now? This time we say or plus sine 45 equals 200G. So or will be 200 times 9.81 minus 1000 over root 2. Tell me what that is, please. 1254? Yeah. Continue? Yeah. Okay, so this one a little bit different. 73 kg. The man is dragging the block. The rope makes an angle of 40 times the ground, and he's pulling the rope at 1,000 newtons, and the block moves at a constant speed. And this time the table is not smooth. It has friction. It has a drag effect. So, draw, and I'll do it. The first question is, what is the friction force? This is the drag force. Okay, did you all draw that? Let's have a look. So, we have our block, 73 kg, and we have our man pulling on it. Again, I went with 45 degrees and 1,000 newtons. And Jerry, what's the verb here?
Resolve.
Very good. You're exactly right. So we resolve. A couple other forces missing. We still have this one here. We still have this one here. And we have this friction force, which is just like a drag force. And the first question is, what is this friction force? And there's a key, Yeah, very good. The key here is that it's moving at a constant speed. And that's really important, because Newton's first law tells us that the total force should be zero if it's moving at constant speed. Because if it's at rest or a constant speed, there's no force. So that's good, because that tells us that the friction on the left must equal the force on the right, and the force acting up must equal the downward force, only because it's moving at constant speed. Okay, so maybe somebody can give me these two answers when they've been calculated, please. Say again, sorry? That's the friction, is it? Yeah.
What if it's not constant speed?
Then we cannot say this.
Then what would be the answer?
I might have an example like that. If I don't say constant speed, I have to at least tell you the acceleration. Okay. Does anyone have the reaction for me, please? What is it, Chrissy?
9.
Exactly 9. 0.023?
Yeah.
Okay. Right, can we continue? Yeah? I think this is, yeah. This is an interesting one now. A weighing scales really measures reaction rather than weight. So, you know what a weighing scales are? So you have something, you put a weight on it and tells you the weight. In fact, the weighing scales is not measuring the weight, believe it or not. It's actually measuring the reaction force. But we know if it's not moving, then the reaction force equals the weight. And also, if it was really a weighing scale, it should tell us the weight in newtons, but instead it tells us in kg, yeah. So it's not really measuring weight, it's measuring mass, and it's not even using the weight to measure it, it's using the reaction force. So anyways, we put a half a kg book on a weighing scale, and then the weighing scale is then lifted vertically up in the air. So somebody lifts it up. What would happen to the reading on the weighing scales? Would it say the book weighs more or less? More. We can kind of picture that if I'm lifting this up, then the weighing scale acts like it's a heavier weight. But why is that, and what would it say? So let's have a look here. First case, it's not moving. So we have our weighing. We have our weighing scales. We place our book on it. This says it's 0.5 G, and this is a reaction force, which also will have to equal 0.5 G to be balanced. So the weighing scale can see that the reaction is 0.5 G, and it knows that the reaction will equal the weight, so it knows that mg equals 0.5 as our G. So it can then get the m is 0.5 then by cancelling the g's. So that's fine. Then we get a problem if it starts to move. So I put my weight on it again. We still have 0.5 G. We still have our reaction force. But if this is moving up at 1 meter per second squared, it means the forces are not balanced. In fact, it must be the case that R is bigger than 0.5 G for it to rise. Yeah? Because otherwise it wouldn't be moving. Now that might seem a bit strange, but if you think about it through the book's point of view, if I put the book on the weighing scale, what forces does it feel? It feels the weight, and it feels the reaction upwards. If it feels itself moving up, it must be because what's pushing it up, the reaction, is bigger than the weight. Okay, so we're happy with that. So what is the total force? Well, the total force will be or minus 0.5 G. That will be the total up force. Yes? Is that okay so far? Is it? You don't look happy, Monica. Not okay or okay? So the up minus the down will give us the total. Yeah. What did Newton tell us in Newton's second law about F? This is ma. That's fine. So Newton says that R equals ma plus 0.5 G. Yeah. Now, that means R will equal 0.5 times 1 plus 0.5 times 9.81. Yeah, if you can give me that, that'd be great, please. Newtons. Now that's what the reaction force really is, and the weighing scale uses this reaction force to calculate the mass. What does the weighing scale think the reaction force is? The weighing scale thinks the reaction force is the same as the weight. Now we know it's not, but this is how it's made. It thinks the weight is the same as the reaction force. So that means it thinks that this is the same as mg. So it will say, okay, the m is 5.405 divided by 9.81. And what's that? 0.55 1. Which is more than 0.5, which is what we thought. So as the weighing scale moves up, it thinks it's heavier. And if it's moving down, likewise, it'll think it'll be lighter. Yeah? Okay, this is kind of a hard one to just understand, but do we have the idea here, or is it okay? Okay, so you might need to write this down, and yeah, that was the last example, so we can write that one down. So have a look here. Okay, nearly have that? Got that? Okay, so we'll try these questions for about, I don't know, 6 or 7 minutes, and then we can take a little break. Yeah, they're pretty much similar to the examples I did, except number 4 is a bit different. So you might even want to leave number 4 until the end, since, well, you'll see when you get it. Which one? Don't be shy.
The last one. 6.
Oh, yeah, everybody has trouble with it.
It's a crazy expensive.
I wouldn't say it's crazy. Here, Jerry, do you want to keep one for Bruce then?